Welcome. This is the second part of the video for the Chapter 1 practice quiz, and I'll cover questions 10 through 14 here. Number 10 is a little misleading because you're just mixing two different strengths of HCl together. So my first solution is 250 centimeters cubed of the 3 molar. So I've got a smaller amount of the more concentrated, which I've tried to show with figure 1 here. And then I'm mixing that with a greater amount of a weaker solution, which I'm trying to show with figure 2 here. So you're mixing different amounts and different strengths. So to come up with our final amount, our final strength, what we need to know is how many moles did we end up with total, and what volume did we end up with total. Well, the volume's easy because this changes to 0.25 decimeters cubed and 0.35 decimeters cubed. So my new volume is 0.600 decimeters cubed. And the moles is just slightly harder because none of these HCl particles escape. It's just that the more crowded ones, the more concentrated ones have a little more space. The less concentrated ones get a little more crowded. So how much is it? It's somewhere between 2 and 3. If it had been equal amounts of each, it would be 2.5. But they're not quite equal amounts. So what I have to do is take my 3 times my 0.25 and see that I have 0.750 moles. Just multiplied these two, and I do the same thing here, and I have 0.70 moles. So that means I have 1.45 moles total in the 600 centimeters cubed total, or 0.6. And so when I divide that, 1.45 divided by 0.6, my new strength is 2.42 moles per decimeter cubed, which seems reasonable because it should be slightly less than the 2.5 since the weaker one had the slightly greater volume. Number 11, you're asked if you have a 55 centimeter cubed sample of salt solution with a concentration of 0.135 moles per decimeter cubed, how many moles of sodium chloride are present? Well, remember, to get your moles, you have to take your concentration times your volume. So when I do that, 0.135 moles per decimeter cubed, and then I'm going to have to change my 55 centimeters, and they don't give me 0.055 as an option, but they do give me 55 centimeters cubed over 1,000 decimeters cubed per centimeter cubed. And they actually don't have the units on there, but this is choice D on the quiz. In number 12, you're given the neutralization equation for sulfuric acid and sodium hydroxide, and you're asked to find the volume of sodium hydroxide needed if it's at 0.25 molars to just neutralize 25 centimeters cubed of 0.125 molar H2SO4. So what I need is the usual in chemistry. I need to know how many moles of H2SO4 this involves, because then I see there's a 2-to-1 molar ratio, and that will give me my moles of NaOH. And when I know my moles of NaOH, I can multiply by the concentration. Actually, I can divide by the concentration. I'll put the 1 decimeter cubed over the moles, which is 0.25, and I'll have my answer. So 0.125 moles per liter, or decimeter cubed, times the 0.025 would be the centimeters cubed changed to the same unit. So 0.125 times 0.025, we're talking 0.003125 moles of H2SO4. And I said it's a 2-to-1 ratio, so that's going to double. So we're talking 0.00625 moles of NaOH. So to change that back, I have to take the 1 decimeter cubed that contains 0.25 moles. That's what that molarity means. So when I divide by the 0.25, I get 0.025, and remember, this is decimeters cubed, and so when you look at the answers are given in centimeters cubed, so when I multiply by 1,000, this is also 25 centimeters cubed. So the correct answer would be A. Okay, so number 13, they're asking about limiting reactant. They tell you have 15 grams of 2-hydroxybenzoic acid, and it's reacted with 15 grams of ethanoic acid. Now, you probably don't know which reactant is which, but you can assume that they've given them to you in the order that they appear in the equation, which is true here. The C7H6O3 is the 2-hydroxybenzoic acid. And it really doesn't matter if you know the correct name for them, because you're going to use the formula to come up with the molar mass for each one. I take the 15 grams of 2-hydroxybenzoic acid, divide by its molar mass of 138.1, and I see that I have 0.1086 moles of this reactant. If I do the same thing with the ethanoic acid, it's got a molar mass of 102.1, so this is 0.1469 moles. But I have to look and see how much product each one will make. In the case of the 2-hydroxybenzoic acid, it's in a 2-to-2 molar ratio, so that molar ratio is going to stay the same. That's how much aspirin it would yield, whereas the other one, it would double because it's in a 2-to-1 ratio. So the 2-hydroxybenzoic acid is definitely our limiting reactant. So that's what question A was looking for. And then B wants to know what's the maximum amount, and when they say, or maximum mass that could be obtained. So I know that the maximum mass is 0.1086 moles. And now they want it in mass. If they say amount, you can leave it as moles. So aspirin at C9H8O4 has a molar mass of 180.17. Oh, there's a decimal there. 180.17 grams per mole. So the maximum amount, the theoretical, should be 19.64 grams. And depending upon how you rounded, I would have taken anything from like 19.57 to 19.81, because if you round off to 0.11 moles, that would push that up to 19.81. So in that range. And then C wants to know what's the percentage yield if the mass obtained was 13.7. So I take the actual experimental value divided by the theoretical or expected times 100%. And my percent yield in this case is 69.8%, going with my 3 sig figs. Number 14 tells you have a metal sulfate with the formula M2SO4. 14.48 grams is dissolved in water, and then it's added to excess barium nitrate, which would be BaNO32, to precipitate all the sulfate ions in the form of barium sulfate. So 9.336 grams of barium sulfate are precipitated. So they want to know the amount of barium sulfate precipitated. So BaSO4, the amount is just a matter of taking the 9.336 grams and changing it to moles. And we know 1 mole of barium sulfate has a mass of 233.4 grams. So all they want for A is 0.0400 moles of BaSO4. Oh, 0.0400. So they're kind of leading you through how to solve this one by asking you the question at a time to get you there. So now they have 0.0400 moles of BaSO4. Since that contains all the sulfate from the first one, then I also know the amount of the sulfate ions. So my amount of sulfate ions, since it's in a 1-to-1 ratio, is also 0.04000 moles of SO4. And so then what that means, and they don't expressly tell you that you need to do this, but it means that I could come up with the relative molar mass of M2SO4 by figuring out if this is how many moles of SO4 I had, then I also know I had 0.08 moles of the metal, but I also could figure out how many grams this is and find out how many grams of the metal I had as well. So I have all the information I need here. I go ahead and take my 0.0400 times the 96.07 grams in a mole of SO4. And when I do that, I end up with 3.84 grams of SO4. So for B, you could either leave it at the 0.04 moles of SO4, or you could change it to grams. Eventually we're going to need it in grams anyway. So then C wants to know what is the relative molar mass of M2SO4. Well, this one, I know that I have 14.48 grams total That's what they told me up on the top. And I also know that I formed 0.04 moles of M2SO4, because if I formed 0.04 moles of SO4, that's also how much of the whole compound we formed. So I could just divide these. My grams divided by moles is my molar mass, and this turns out to be 362 grams per mole. And then D wants to know the relative atomic mass of M. Well, I know that I had 14.48 minus the 3.84 tells me how many grams I have. So 14.48 minus the 3.84, I have 10.64 grams, and that's in 0.0800 moles, because the metal is in a 2-to-1 ratio. So now when I divide that by 0.08, I come up with atomic mass for the metal of 133 grams per mole. And if you look that up, you see that that's cesium.